Hello. This is a continuation of the history of deep learning. It seems in this class, this has to be updated pretty much every year. And the fundamental question we're still continuing to think about is there a Moore's law of AI in progress at the moment? So this is going to cover basically from about 2020 through the current situation. And the first thing I want to talk about is wave to vec. Now, wave to vec is important because it's a model of how children learn the phonemes of their language just by listening to it. Nobody's telling the one-year-old how to spell things phonetically, and yet it's learning these phonetic, seems to be learning phonetic symbols. So wave to vec is a system that learns a symbolic representation, a symbolic transcription of speech, of audio, just by listening to the audio. So it listens to the audio and it categorizes, it creates discrete symbols for different pieces of the audio. And they end up not being phonemes in the sense that we're used to phonemes, the way you would spell words in English, for example, but they are discrete tokens. And once this system has learned to transcribe speech into discrete tokens, it can use those discrete tokens as the foundation for speech, for learning real speech recognition, real transcription of audio into text based on its pre-learned transcription of audio into these discrete symbols. And the fundamental result is the amount of labeled text, labeled speech, the amount of speech that you need to associate with its transcription into text is reduced by a factor of 100. They can take 1 hour of labeled speech and be competitive with what other speech systems learn with 100 hours of labeled speech. So there's a huge boost in the data efficiency of learning to do speech recognition by doing this pre-training on learning transcripts. So that was a while ago, that from Facebook. Then about 6 months later, they did this generative spoken language model. So here what's going on is they take, it's going to be all trained just from audio. No, nothing's going to be labeled. So just from audio, the previous system transcribed that audio into a sequence of symbols. Now we're going to take that sequence of symbols and develop a model of those sequences, the same way you would develop a model of language. It's just like what GPT-3 does with words, but now we're doing that with this sequence of symbols that's derived just from speech signal alone. So just from a speech signal alone, you develop this model of the sequence, and then you can generate speech by generating those tokens, just like you would generate text. And the point here is the system just from speech is now learning higher level things like grammaticality, like the words and grammaticality. And it's also learning prosody, how to express emphasis and emotional content. I'll make available the recordings of this, the examples of speech generation here. It's really very impressive. Okay, July 21. OpenAI introduced Codex. This is another, it's based on GPT-3, or it starts with GPT-3. And what it's trained on is a large corpus of computer code in various languages and various APIs for various applications. And that computer code contains comments, English comments. So it's trained on English comments associated with code, and then it's using various tricks. What it's designed to do is take an English request and translate it into code. And it's really very impressive and kind of creepy in the sense of what it can do. You can train it to interface to Microsoft Word or various other applications. And there's a published version called Copilot, and it seems the most likely application of this is not the design of deep code. It's not going to invent a new algorithm, but it will tell you how to do a loop in some particular language. So it has the potential to replace Stack Overflow if you want to know how to do X in language Y. So this is a sort of a startling development. Okay, CLIP, Contrastive Language Image Pre-training. This is important for various reasons. One is it's a really strong demonstration of this idea of contrastive learning, which we're going to talk about. This course is really going to be emphasizing the fundamentals. So we're going to be emphasizing architectural ideas rather than particular applications. So we'll be talking about particular applications, but this contrastive learning is a very general learning technique, and CLIP is a really clear paradigmatic example of that. So what we do here is we take a large corpus of images together with text, which is scraped off the web, right? If you have a URL pointing to an image, the text of that URL associates that image with some text. And what CLIP does is it computes a way to embed text as a vector and embed the image as a vector such that the two are sort of carrying the mutual information. The image, in some sense, predicts what the text is, and the text predicts what the image is. So it's a kind of co-embedding of the two things based on this contrastive learning methodology. And so what CLIP was applied to in the beginning was zero-shot image classification. So you scrape this huge corpus of images and text, train this embedding, and then you can take an image, and suppose you want to solve ImageNet, which is to classify this image as one of 1,000 categories. What you can do is construct the sentence, this is a picture of a fish, or this is a picture of a dog. And you take those sentences and you embed them, and you take the image and you embed it, and you see which sentence has an embedding closest to the embedding of the image, and that can be used to classify the image. So is this image more compatible with this is an image of a fish text, or is it more compatible with this is an image of a dog text? So here's an example of classifying food type. So you show it this picture and you evaluate the score of how much the embedding of this sentence, a photo of a guacamole, a type of food, how close is this to the embedding of this image in this co-embedding? And you can do this for various other kinds of food, and this embedding is closest, and then you can use that to classify the image. And the big point here was that this is much more robust because you trained it in this sort of self-supervised way on this huge corpus of text and image. It can solve all kinds of text-image relation problems. So you can build classifiers for various other things using this zero-shot methodology. This also sort of gave rise to what's called prompt engineering, right? How do you design the sentence that you're going to use to classify the images? And prompt engineering has really taken off. And that's almost an architectural idea now, this idea of designing inputs, prompts to large pre-trained models. Okay, now this is huge. DALL-E. I'm sure everyone's familiar with this, but you may not be familiar that this is really based on CLIP also, right? So both versions of DALL-E that came out in January 2021 and the DALL-E that came out April of this year are both using CLIP's sort of co-embeddings of image and text. DALL-E came out, the first DALL-E came out sort of at the same time as CLIP. And what DALL-E is trained to do is to take a piece of text and generate an image that is compatible with the embedding of that text. So you can type in an illustration of a baby daikon radish in a tutu walking a dog, and you get out these pictures. This was based on an autoregressive model, an autoregressive image model. And DALL-E 2 is generating dramatically better pictures and is really scaring artists, and is, this is really shocking. These images are really shocking. And there's a major architectural difference here based on something called diffusion models. So diffusion models, they were introduced in 2015, a long time ago, but they've just recently been very prominent. They're taking over lots of things. And we'll talk about the difference between a diffusion model and an autoregressive model. DALL-E 1 was this autoregressive thing. It's like GPT-3. It's generating sort of a little image piece at a time. A diffusion model is fundamentally different. It's generating the whole image simultaneously by this thing called a diffusion process. And that's going to be a new component in the class as of 2022. Another thing that's happened that seems very important is this chain of thought prompting. So this is January of this year. So the idea is this is part of prompt engineering. How do you give a prompt, in this case to a language model, to make it do what you want it to do? So here's an example of numerical question answering. So there's this problem. Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? And so what you're doing here is you're giving GPT-3 a prompt. Now, GPT-3 had this very shocking property that if you gave it English-German pairs, it would generalize that to translation. Here you're giving it question-answer pairs and hoping that GPT-3 can generalize to solving numerical problems. So you give it this example of solving a numerical problem, and then you give it a numerical problem, and then you have it generate the answer. And in this case, it generates the wrong answer. But now if you change the training data, the prompt training data, this is GPT-3 is still there. You're just changing the prompt. You change the prompt to have a chain of thought, sort of the answer involves going through step by step the reasoning to get the answer. So this is just changing the prompt. And now when you change the prompt to show explicit reasoning, GPT-3 generates the right answer. So then in June of this year, there was just a blog post that said, gee, you know, all you have to do is prompt GPT-3 with a prompt that says, take it step by step. And this one simple prompt causes GPT-3 to generate step by step descriptions of reasoning, and that applies across a wide variety of things that involve step by step reasoning. And this is fascinating to me because it's, you know, Kahneman has talked about solving things fast and slow. And this is sort of prompting GPT-3 to take it slow, right? To elicit steps of reasoning. This seems to me to be a very important and will continue to be a very important development. I just want to end this on something that happened just 2 weeks ago. As of this happened in mid or early September. DeepMind demonstrated humanoid soccer playing at a really high level of competence, and this was done on a simulation platform called Mujoko. And I don't know if you've seen, many of you may have seen parkour videos or learning to walk videos where humanoid robots learn to run and walk and do parkour, and they're really pathetic. Somehow, you know, this robot that's learned to walk is waving its arm up in the air or doing really weird things. So this demonstration, it cheats a little bit in the sense that it uses motion capture as a foundation for the training, but then it uses reinforcement learning to develop humanoid robotic control that plays competent 2-on-2 soccer. So this is in my opinion, this is a really major advance in reinforcement learning for robotic control. It's based on simulation, but it's still, this is a big advance in the Mojoko world. So I'll just end saying that in this class is fundamentals of deep learning. We're going to emphasize the general ideas, right? The architecture and the general ideas of learning. And the applications will be sort of filling in, how these things are impacting AI. And I want to, again, revisit the idea of whether there's a Moore's law of AI. So since, I don't know, 2009, I've been saying that there seems to be a Moore's law of AI. And back in 2009, I was saying if there is if we're making significant advance, whatever that means, every year, things are going to get really interesting in 10 years. And they have. I mean, we're not quite at human level AI, or we don't really know how far we are from human level AI, but it feels like the Moore's law has continued. And I keep expecting some kind of plateau that's waiting for the next breakthrough. But there are so many people doing so much research that it feels like it's just getting faster. And I'll end there.